What do the sound you hear when you open a can of soda and the odor you smell when you open a bottle of cleaner have in common? Although you may not realize it, your senses detect that opening these containers causes chemicals to come out of solution. In this program, you will learn about solutions and how they form. You will become familiar with various ways to calculate solution concentrations. In addition, you will learn what colligative properties of solutions are and how solutes influence them. Two or more combined substances that do not react form a mixture. The word substance is a generic term describing matter that has definite composition, such as an element or a compound. Mixtures can be either heterogeneous or homogeneous. In a heterogeneous mixture, substances do not occur uniformly throughout the mixture. Therefore, substances in heterogeneous mixtures can in essence be distinguished from one another. A chocolate chip cookie can be considered a heterogeneous mixture because some substances, in this case chocolate chips, are not evenly distributed throughout the cookie. For example, you may have one chocolate chip in your first bite of cookie, but none in the second bite. Unlike heterogeneous mixtures, the substances in homogeneous mixtures occur uniformly throughout the mixture. If you take several samples of a solution, you will find that the proportions of the substances within each sample are equal. In addition, the substances are not readily distinguished from one another. In fact, the substances in solutions remain together when run through a filter. Soda is an example of a homogeneous mixture because it contains several ingredients, including carbonated water, sugar, and phosphoric acid mixed uniformly throughout the soda. Your taste buds attest to the uniform distribution of this solution, since the first gulp of soda tastes the same as the last. Soda is also an example of a solution. Any homogeneous mixture is a solution. Heterogeneous mixtures cannot be solutions, since the substances in them are not uniformly mixed. For solutions to form, one or more substances must dissolve in a medium, which is often a liquid. Using Kool-Aid as an example of a solution, you see that the Kool-Aid powder dissolves in water when stirred. Since the powder dissolves in water, the powder is called a solute. A solute is any substance that dissolves when making a solution. The medium in which a solute dissolves is called a solvent. Water is the solvent in this example. A solute that dissolves in a specific solvent is said to be soluble in that solvent. As you have just seen, Kool-Aid powder is soluble in water. However, not all substances dissolve to form solutions in a given solvent. Compare what happens when you place a water-soluble vitamin C tablet into a beaker of water and another into a beaker of vegetable oil. The vitamin C tablet begins dissolving shortly after being placed into the water. In contrast, the vitamin C tablet placed in the beaker of vegetable oil does not dissolve, even when prodded with a stirring rod. A solute that does not dissolve in a specific solvent is said to be insoluble in that solvent. In this example, vitamin C is insoluble in vegetable oil. Solutions can be liquids, gases, or solids. Classification of a solution is based on the state of matter of the solution after the solute and the solvent mix. For instance, liquid solvents are capable of dissolving gases, solids, and other liquids to form liquid solutions. In fact, soda is a good example where the three states of matter are blended into one state. to produce carbonated water, which is the main ingredient in most sodas. Carbon dioxide gas and water are bottled under great pressure, causing the gas to dissolve into the water. To sweeten the soda, solid sugar and liquid corn syrup are dissolved into the liquid soda solution. Since this solution and many other solutions contain water as the solvent, a term distinguishing these solutions from solutions where water is not the solvent is used. Liquid solutions that have water as the solvent, such as soda, are called aqueous solutions. Liquid solutions that contain a different solvent are simply called liquid solutions. Not all liquids dissolve into one another to form a solution. You are probably quite familiar with the fact that oil and water do not mix. The rainbow-colored beads or streaks you see on the pavement after a rainstorm result from leaked engine oil not dissolving into the water on the pavement. Liquids such as these that do not dissolve are said to be immiscible. Liquids that dissolve, such as acetic acid and water, which make the vinegar solution used to color Easter eggs, are miscible. Liquids capable of dissolving into one another in any amount are said to be completely miscible. For example, 50 milliliters of acetic acid dissolve in 5 milliliters of water as easily as 5 milliliters of acetic acid dissolve in 50 milliliters of water. Many liquid solutions are common and familiar. However, solutions can also be solids or gases. Remember that the state of matter of a solution is determined once the solute and solvent are mixed. For example, 18-karat gold is a solid solution composed of 75% gold and 25% silver. In order to blend pure gold and pure silver into a solution, the metals must be melted, mixed, and then cooled. Once cooled, the blend of the two metals is a solid solution in which the gold and silver atoms remain fixed in a uniform distribution. Metals, such as silver and gold, are often combined into solid solutions to create products with properties different from the pure metals composing the solution. The resulting solution is called an alloy. For example, pure gold is a soft metal. Consequently, jewelry made of pure gold bends, twists, and scratches easily. However, when gold is mixed with silver or nickel, the resulting alloy is much harder. Other common alloys are used in chromoly bike frames, stainless steel pots, sterling silver jewelry, and brass instruments. Examples of gaseous solutions include the compressed air one breathes while scuba diving and the laughing gas administered during dental surgery. Substances in a gaseous solution are uniformly distributed and constantly in motion. Any homogeneous mixture of gases that do not react together form a solution. As with all solutions, the properties of the solution can differ from the properties of the substances forming the solution. Now that you know what solutions are, take a look at how solutions form. This demonstration shows how a solid solute dissolves in a liquid solvent. Here you see a crystal lattice of the sodium chloride solute begin to dissolve when placed in water. Since water is a polar molecule, its oppositely charged ends can overcome attractions keeping the ions within the salt crystal together. The partial positive charge on the hydrogen end of several water molecules draws the negative chloride ion from the solute, and the partial negative charge on the oxygen atom in several water molecules draws the positive sodium ion from the solute. As a result, The sodium and chloride ions are stripped from the crystal lattice and enter the solution. As the ions enter the solution, intermolecular attractions between water molecules are broken, providing room for the ions within the solvent. Once the ions are in solution, intermolecular attractions form among the ions and the water molecules in a process called solvation. When water is the solvent, as in this example, the process of solvation is called hydration. Here is a summary of the three processes that occur when a solid solute dissolves in solution. Although the processes are discussed and summarized in a particular order, they occur simultaneously when forming a solution. In one process, the solute breaks apart. If the solute is an ionic compound, such as sodium chloride, attractions among ions are overcome. If the solute is a molecular substance, such as the sugar glucose, attractions among the individual molecules are overcome. In a second process, attractions among molecules composing the solvent must be broken to provide space for the solute. In a third process, attractions form among the solvent particles and solute particles to form the solution. In step 1, energy is required to break the attractive forces holding the solute together. Energy is also required in step 2 to break the attractive forces within the solvent, which provides space for the solute. Processes requiring energy in the form of heat, such as those occurring in steps 1 and 2, are called endothermic or energy-absorbing processes. In contrast, the process in step 3 releases energy as attractions form between solvent and solute particles. Energy-releasing processes are called exothermic processes. If the combined amount of energy required to break the attractions within the solute and within the solvent is greater than the energy released when new attractions form between solute and solvent, then the formation of the solution is endothermic. If the opposite situation occurs, where the energy required to break the attractions within the solute and within the solvent is less than the energy released when attractions form between solute and solvent, then solution formation is exothermic. A solution formed through an exothermic reaction, which can be made easily in your lab, is shown here. The solute, calcium chloride, is added to 100 milliliters of room temperature water in a beaker. As calcium chloride dissolves, you can feel heat coming from the solution, as the increasing temperature reading indicates. An endothermic reaction occurs when making an ammonium nitrate solution. Ammonium nitrate dissolves when placed into 100 milliliters of water. As it dissolves, the absorbed energy causes the beaker to feel cold to the touch. The decreasing temperature reading indicates the cooling of the solution. You may be more familiar with this endothermic process than you realize if you have ever used a cold pack to reduce the soreness and swelling of an injury. Imagine wanting to increase how quickly the ammonium nitrate mentioned in the last scene dissolves. How can you influence this? There are 3 factors you can use that affect how quickly a solid dissolves. These factors are temperature, stirring, and surface area. Temperature has a fairly consistent effect on the dissolving rate of a solid. When a solid solute is placed in a liquid solvent and subsequently heated, the increase in kinetic energy from the heat causes the solvent molecules to move quickly. As a result, the solvent molecules strike the solute's surface and generally strip the particles off the solute more rapidly at higher temperatures. Therefore, heating a solvent usually causes the solute to dissolve more quickly. Another way to increase how quickly a solid dissolves is to stir the solvent. Stirring increases how fast a solid dissolves because stirring moves stripped solute particles away from the solid and into solution. If a solid dissolves without being stirred, the stripped solute tends to linger near the solid. This hinders solvent molecules from approaching the solid, therefore dissolving is slow. Stirring moves dissolved solute away from the solid, allowing the solvent molecules to quickly strip more solute from the solid surface. You just saw that dissolving occurs when solvent particles strip solute particles from the surface of a solid. Increasing the surface area of a solute provides a larger surface upon which the solvent can act. As a result, the rate at which the solid dissolves increases. If you're given a salt block, how could you increase the surface area of the block so it could dissolve more quickly? One answer is to break the salt block into many smaller pieces. Although the total amount of salt remains the same, the many smaller pieces of salt have a combined surface area larger than the single block. Consequently, the smaller pieces provide a larger total surface area on which the solvent can pull off solute at any time. The more pieces you break off the block, the greater the total surface area. Therefore, when you put the pieces of salt into the solvent, they dissolve more quickly than would a large block of salt. The amount of solute dissolved in an amount of solvent is referred to as a solution's concentration. Sometimes your senses can detect the concentration of solutions. If you consider cranberry juice too tart, then the juice is too concentrated for your preference. Three terms describe the relative amount of solute within a solution: unsaturated, saturated, and supersaturated. A solution in which solute particles continue to dissolve in the solvent is said to be unsaturated. For example, bags of sweetener poured into a glass of unsaturated sun tea dissolve. If you continue adding more sweetener, the sweetener eventually stops dissolving. At this point, the solution contains as much solute as the solvent can hold at a specific temperature, and the solution is saturated. Thus, addition of solute to a saturated solution does not cause more solute to dissolve. However, a solution can sometimes be supersaturated, meaning that the solution holds more solute than a saturated solution at a specific temperature. Supersaturated solutions occur only under manipulated conditions, when the temperature of the solvent is raised to allow more solute to dissolve. The solution is then slowly cooled so that solute crystals do not immediately form, as is shown in this example of sodium acetate. Supersaturated solutions are unstable. It takes just a small crystal or a tap on the container to make the excess solute come out of solution, which returns the solution to a saturated solution. Solution concentrations usually need to be measured more precisely than in the relative terms just discussed. A patient admitted into a hospital for dehydration needs an IV to hydrate them. It is important to know the exact concentration of the saline solution in the IV, because too high of a saline solution could further dehydrate the patient. Without knowing exact concentrations, how would you determine what is too high? There are a number of ways to determine solution concentration. One way is to determine the solution's molarity, which is designated by a capital M. Molarity is expressed as the number of moles of solute in 1 liter of solution. You may remember from your previous chemistry studies that the number of particles in a mole of anything, including various solutes, is 6.02 times 10 to the 23rd. When determining the molarity of a solution, remember to express the answer in units of molarity, moles of solute per liter of solution. How would you determine the molarity of a 100 milliliter solution that contains 6 grams of potassium dichromate? Notice that this example begins with 6 grams of the solute per 100 milliliters of solution, instead of moles of solute per liter of solution. Therefore, you need to convert the 6 grams of potassium dichromate to moles. To convert grams to moles, you must first determine the molar mass of the solute. Molar mass tells how much 1 mole of a substance weighs and is expressed in grams per mole. Calculate the molar mass by adding the molar masses of all the atoms that comprise the solute. Each potassium atom has a mass of 39.10 grams per mole. Each of the 2 chromium atoms has a molar mass of 51.99 grams per mole, and each of the 7 oxygen atoms has a mass of 16 grams per mole. Therefore, the molar mass for potassium dichromate is 294.18 grams per mole. Dividing the 6 grams of potassium dichromate by its molar mass gives a total of 0.0204 moles of potassium dichromate. The next step to determine molarity in this example is to convert milliliters to liters. The 100 milliliters of solution need to be converted to liters. Make the conversion using the conversion factor 1,000 milliliters equal 1 liter. To be sure the equation is set up correctly, make sure the units cross-cancel for everything but moles in the numerator and liters in the denominator. The calculation shows the molarity of this potassium dichromate solution is 0.204 moles of potassium dichromate per liter. When making a solution measured in molarity, first place the solute into a volumetric flask. Then add roughly 25% of the desired solvent to the flask. Swirl the flask until the solute dissolves, then add the solvent until the solution reaches the desired amount. A second way to express solution concentration is molality, which is denoted by a lowercase italicized m. Molality expresses the number of moles of solute per kilogram of solvent. Note that the units in the denominator position differ between molarity and molality. Molality measures the mass of solvent, whereas molarity measures the volume of the entire solution. What is the molality of a solution containing 125 grams of sodium chloride in 2 kilograms of water? To determine the molality, first determine the molar mass of sodium chloride, which is 58.44 grams per mole. Converting grams to moles, you see that 125 grams of sodium chloride equal 2.139 moles of sodium chloride. Now set up the remainder of the problem so that your answer will be left in units of molality, or moles of solute per kilogram of solvent. This is simply done by placing the 2 kilograms of water in the denominator position. The molal concentration of this sodium chloride solution is 1.07 moles of sodium chloride per kilogram of water. Mole fraction is a third way to express a solution's concentration, and it is represented by the Greek symbol chi. The mole fraction is the number of moles of one component, either the solute or the solvent, divided by the total moles of the solution. Total moles of the solution equals the number of moles of solute plus the number of moles of solvent. A subscript indicating whether the solute fraction or the solvent fraction is being solved for is placed after chi. For example, if the mole fraction of a solute is being determined, the equation is moles of solute divided by total moles of solution, and the equation is denoted as chi with the term solute written as a subscript. If the mole fraction of a solvent is being determined, the equation is moles of solvent divided by total moles of solution. This equation indicates what portion or fraction of the entire solution is solvent. To verify that your answer is correct, make sure the solvent mole fraction and the solute mole fraction total 1 when added. This ensures that each part of the solution was taken into account. Before calculating mole fractions, let's use a familiar example of fractions to illustrate the concept. Imagine that you and your friends go to the movies. You notice that the audience is composed of a mixture of males and females. You count 80 people in the audience, 44 males and 36 females. The audience fraction of males is 44 out of 80, or 0.55, and the audience fraction of females is 36 out of 80, or 0.45. When the audience fractions are added, their sum equals 1. Adding each component is a good way to determine if your work is correct. Here is a sample of a problem using mole fractions. Find the mole fraction of the solute in a solution prepared by mixing 53 grams of sodium acetate into 100 milliliters of water. Determine the number of moles of sodium acetate and water. The composition of sodium acetate is NaC2H3O2. Therefore, its molar mass is 82.04 grams per mole. Using the conversion factor 82.04 grams per mole, calculate the number of moles in 53 grams of sodium acetate. The number of moles is 0.6460. Next, convert 100 milliliters of water to moles of water. Remember that the density of water is 1 gram per milliliter. Therefore, the conversion factor equating 1 milliliter of water to 1 gram of water can be used because 1,000 milliliters equal 1 liter and 1,000 grams equal 1 kilogram. Now the units are in terms of mass and not volume, but you still need to determine the number of moles of water. The composition of water is H2O. Therefore, its molar mass is 18.02 grams per mole. Finishing the conversion of 100 milliliters of water into moles of water gives 5.549 moles. In other words, there are roughly 5.5 moles of water in 100 milliliters of water. Now that you know the number of moles of solute and solvent, you can determine the mole fractions of each in the next scene. Adding the number of moles of water with the number of moles of sodium acetate determined in the previous scene gives the total number of moles of solution. This value, which becomes the denominator when determining mole fractions, equals 6.195. Now find the mole fraction for sodium acetate. Simply plug the number of moles you just calculated for sodium acetate, 0.6460, into the equation for the mole fraction of the solute. You see that 0.6460 divided by 6.195 equals 0.1043, which is the mole fraction of sodium acetate. You can determine the mole fraction of the solvent at this point in one of two ways. One way to determine the mole fraction of water is by dividing the number of moles of water, 5.549, by the total moles of solution, 6.195. The mole fraction of water is 0.8957. To ensure that your answer is correct, add both mole fractions together. If their sum equals 1, then you have done the calculations correctly. The sum of 0.1043 and 0.8957 equals 1. Therefore, you can be assured you solved this problem correctly. The other way to determine the mole fraction of water is to subtract the value of the solute's mole fraction from 1. Subtracting 0.1043 from 1 gives a solvent mole fraction of 0.8957. Although the second method is quicker, there is no way to guarantee that your calculations are correct. Remember that the original question only asks for the mole fraction for the solute, which was calculated to be 0.1043. Percent solution is the fourth and final way solution concentration will be presented in this program. However, you will learn two ways of calculating percent solution. The first, called percent solution by volume, is rather simple to calculate and is used when both the solute and solvent are liquids, such as methanol and water. Percent solution by volume measures the volume of a solute in relation to the volume of the entire solution. The fraction is converted to a percent by multiplying it by 100%. Suppose you add enough water to 25 milliliters of methanol to bring the final solution volume to 125 milliliters. What is the percent methanol by volume? To answer this question, list the details that you know. 1. The volume of solute is 25 milliliters. 2. The volume of solution is 125 milliliters. The volume of solute divided by the total volume of solution multiplied by 100% gives a value of 20%. Since the units for volume are the same, they cancel. This solution contains 20% methanol. Remember to indicate that this measurement of percent solution is volume to volume, which is abbreviated as V over V. When working with a solid solute in a liquid solvent, percent solution can be expressed in terms of mass of solute in grams over volume of solution in milliliters times 100%. It is often simple and convenient to weigh the quantity of solute needed to make a solution. For example, you are asked to make an aqueous sucrose solution that is 3% mass by volume. This indicates that 100 milliliters of solution contain 3 grams of sucrose. To make this solution, place the 3 grams of sucrose into a flask and add enough water to bring the volume to 100 milliliters. Whenever dealing with percent solutions, be sure to report the percent solution in the appropriate units. Notice that mass per volume is abbreviated as M over V. Sometimes solutions are more concentrated than needed or desired. It is rather simple to dilute solutions. In fact, you have probably done this often. If cranberry juice is too tart, you add water to make it less concentrated. To dilute a solution, add more solvent. As the example shows, the amount of solvent in the dilute solution increases, while the amount of solute remains unchanged. Consequently, the solution becomes less concentrated. You can use your knowledge of solution concentrations, including mole fractions, to verify this concept. In the concentrated solution, there are 3 moles of solute per 7 moles of solution. The mole fraction of the solute is therefore 0.4. In the dilute solution, the additional moles of solvent bring the total moles of solution to 15. Therefore, the mole fraction of solute is 3 moles of solute divided by 15 moles of solution, which equals 0.2. You can see how the addition of solvent molecules changes the proportions of the solution. Since the number of moles of solute does not change when making dilutions, a simple ratio can be used to determine how to prepare a dilute solution from a more concentrated solution. For example, suppose the all-purpose cleanser you use to clean the lab comes in a concentrated form called a stock solution. The label on the side of the bottle says to dilute the contents to a 0.6 molar solution before using. The label indicates that the cleaning solution is 3 molar. Therefore, you know that there are 3 moles of solute per liter of solution. Since the moles of solute do not change when making dilutions, you can use the equation M1 times V1 equals M2 times V2 to relate the molarity and volume of a concentrated solution to the molarity and volume of a desired diluted solution. Recognize that canceling the units in the given equation leads to an equation stating that the number of moles in the concentrated solution equals the number of moles in the dilute solution. The M1 times V1 equals M2 times V2 equation allows you to determine the volume of the concentrated solution required to make the dilute solution. You are asked to prepare 500 milliliters of a 0.6 molar solution from the 3 molar stock solution of lab cleanser. How do you prepare this solution? You know the desired volume of the dilute solution, which is designated as V2, is 500 milliliters, and the molarity of the dilute solution, which is designated as M2, is 0.6 moles per liter. M1 equals the molarity of the concentrated solution, and in this example, M1 equals 3 moles per liter. Rearrange the equation to solve for V1. Then substitute the numbers into their appropriate places in the equation. V1 tells you the amount of the stock solution needed to make the dilution. The calculation gives you the answer 100 milliliters. Therefore, to make the desired solution, place 100 milliliters of the stock solution into a 500 milliliter container and add enough water to bring the final volume to 500 milliliters. At this point, you have 500 milliliters of a 0.6 molar solution. If the volume of the solution must be precise, use a volumetric flask and pipette. Earlier in the program, you learned that properties of a solution can differ from the properties of the substances that comprise the solution. This was covered in the discussion of alloys. However, some properties of solutions depend on the number of solute particles in solution and not the substances involved in the solution. The properties that depend on the number of solute particles are collectively called colligative properties. Colligative properties of solutions are vapor pressure reduction, boiling point elevation, freezing point depression, and osmotic pressure, each of which you will learn about in the next few scenes. The first colligative property you will investigate is vapor pressure reduction. Here you see a liquid solvent placed in a container, which is subsequently sealed. A short time later, some of the solvent molecules leave the liquid state, becoming gas molecules in a process called evaporation. Soon, some of these gas molecules return to the liquid state in a process called condensation. Eventually, a state of equilibrium occurs in which the rate of evaporation equals the rate of condensation. At equilibrium, there is no net change in the number of molecules in the gas and liquid phases, although molecules continually evaporate and condense. The pressure of the gas molecules within the container at this time is known as vapor pressure. Adding a non-volatile solute, such as sugar or salt, to the solvent reduces the solvent's vapor pressure. The term non-volatile means that the solute does not evaporate into a gas at the temperature of the solution. Although the non-volatile solute mixes throughout the solution, it is the particles at the surface of the solution that have the greatest effect on vapor pressure. The solute particles at the surface displace some solvent particles, causing fewer solvent molecules to be located at the solution's surface. Consequently, fewer solvent particles can evaporate, since evaporation occurs at the surface of the solution. This in turn reduces vapor pressure in the container, because fewer solvent molecules exist in the gas phase. The reduction in vapor pressure is directly proportional to the number of solute particles in the solvent once the solute dissolves. For example, adding the salt sodium chloride to a solvent reduces the vapor pressure twice as much as adding the same concentration of the sugar sucrose to a solvent, as adding the same concentration of the sugar sucrose to a solvent. The reason the salt lowers the vapor pressure more than sugar is because sodium chloride separates into its two constituent ions, sodium ions and chloride ions, when it dissolves. Therefore, 1 mole of the solute sodium chloride yields 2 moles of particles, one of which is a mole of sodium ions, and the other of which is a mole of chloride ions. In contrast, when sucrose dissolves, individual sucrose molecules separate from the solute. Therefore, only 1 mole of sucrose particles enters the solution for each mole of sucrose. Since 2 moles enter solution when sodium chloride dissolves, compared to 1 mole that enters solution when sucrose dissolves, the container with the sodium chloride solution has half the vapor pressure of the container with the sucrose solution. This is because 2 moles of ions from sodium chloride inhibit twice as many solvent particles at the solution's surface from evaporating as 1 mole of sucrose. Another colligative property is boiling point elevation. Boiling point is defined as the temperature at which the vapor pressure of a liquid equals the pressure of the atmosphere. Water placed in a pot on the stove has a lower vapor pressure than the surrounding atmosphere. Therefore, the water does not boil. Heating the water causes water molecules to evaporate from the pot more quickly. Consequently, the vapor pressure of water increases until the water begins to boil. When the water boils, the vapor pressure within the pot equals the pressure of the atmosphere. In previous scenes, you learned that the addition of a non-volatile solute to a solvent decreases vapor pressure. The reduction of vapor pressure in turn affects boiling point, because more heat is required in the presence of a non-volatile solute to raise the vapor pressure enough to equal the pressure of the atmosphere. Consequently, a higher temperature is required to make the solvent boil, which can be seen in the example and on the graph showing the phase diagram of pure water. In this diagram, the solid blue line indicates the vapor pressure of pure water. The lower vapor pressure of an aqueous solution containing a non-volatile solute is shown in red. Notice that the line representing the lower vapor pressure shows the solution has a higher boiling point than that of pure water. The change in boiling point temperature can be calculated using the equation delta Tb equals Kbm. Delta Tb is the number of degrees the boiling point increases. Kb is the molal boiling point elevation constant, which is expressed in terms of degrees Celsius per molal concentration. Each solvent has a specific Kb value regardless of the solutes added, and Kb values for various solvents can be found in many textbooks. In addition, M is the concentration of the solution measured in molality. Remember that molality measures a solution's concentration in terms of number of moles of solute per kilogram of solvent. Engine coolant, which is a solution of ethylene glycol and water, is an excellent example of a non-volatile solute used to elevate the boiling point of water. Coolant is used in car radiators to prevent them from overheating on hot summer days. Let's calculate the boiling point for a solution containing 5.49 moles of ethylene glycol in 1,400 grams of water. The first step is to determine the molality of the solution. Dividing 5.49 moles by 1,400 grams gives 0.00392 moles of solute per gram of solvent. Since molality is expressed in terms of moles of solute per kilogram of solvent, this answer must be multiplied by the conversion factor 1,000 grams over 1 kilogram. The molality of this solution equals 3.92 moles per kilogram. Now you're ready to insert the known values into the boiling point elevation equation. According to the chart, the Kb value for water is 0.512 degrees Celsius per molal concentration. Multiplying 0.512 degrees Celsius per molal by 3.92 molal equals 2.01 degrees Celsius, which is the temperature difference between the boiling point of pure water and a 3.92 molal solution of ethylene glycol. Adding 2.01 degrees to water's boiling point, which at standard pressure is 100 degrees Celsius, gives an elevated boiling point of 102.01 degrees Celsius. Adding 5.49 moles of ethylene glycol to 1,400 grams of water causes the solution to boil at 102.01 degrees Celsius. Freezing point depression is another colligative property. Freezing point is the temperature at which a liquid becomes a solid. During the freezing process, a substance changes from a loosely organized state to a highly organized state. As a substance changes from a liquid to a solid, intermolecular attractions between molecules become fixed. At 0 degrees Celsius and 1 atmosphere of pressure, water freezes and turns to ice. The addition of a non-volatile solute to a solvent inhibits the ability of the solvent to form an organized structure. Therefore, the solute must be moved out of the solvent particle's way in order for the solvent to freeze out of solution. The temperature of the solution must be lowered enough that the solvent molecules have a greater chance of forming attractions strong enough to hold the solvent particles together without the interference of the solute particles. When the appropriate temperature is reached, a solid made of only solvent particles forms. Engine coolant is not only used as a non-volatile solute to prevent car radiators from boiling over. It is also called antifreeze, and as the name indicates, antifreeze prevents the water in a car's radiator from freezing during icy cold winters. The equation for freezing point depression is similar to the equation for boiling point elevation. Delta Tf equals Kfm. Kf is the mole freezing point depression constant, and you can find the Kf value for various solvents in many textbooks. Just as in the boiling point elevation equation, the concentration of the solution is measured in molality. Calculate the freezing point of the solution containing 150 grams of ethylene glycol in 0.75 kilograms of water. Remember that you must first convert the 150 grams of antifreeze to moles in order to determine the solution's molality. The molecular formula of ethylene glycol is C2H6O2. Therefore, its molar mass is 62.07 grams per mole. Dividing 150 grams by 62.07 grams per mole gives a value of 2.417 moles of ethylene glycol. The next step in solving this problem is to determine the concentration of this solution in units of molality. Because the amount of solvent is already given in kilograms, just divide the number of moles of ethylene glycol by the number of kilograms of water. Dividing 2.417 moles by 0.75 kilograms of water gives a molality of 3.2 moles of solute per kilogram of solvent. Now substitute the known values into the freezing point depression equation and multiply. From the chart, you determine the Kf value for water is 1.86 degrees Celsius per molal, and you just calculated the molality. The answer shows that 150 grams of antifreeze in 0.75 kilograms of water lowers the freezing point 6 degrees to a temperature of -6 degrees Celsius. Adding a non-volatile solute like ethylene glycol to a solvent increases the temperature range in which a solution remains a liquid. The temperature range increases because the non-volatile solute elevates the boiling point and depresses the freezing point of a solvent. This relationship can be seen in this graph. The graph also shows the relationship between the amount of solute in a solution and the changes in the temperatures at which the solution boils and freezes. Since Kf and Kb values are constant for each solvent, the change in the temperature at which a solution boils and freezes is directly proportional to the molality of the solute. For example, doubling the amount of solute doubles the amount of change in freezing point depression and boiling point elevation, and a tripling of the amount of solute triples the amount of temperature change. The last colligative property you'll examine is osmotic pressure, which is designated as pi. This system will be used to illustrate the concept of osmosis and osmotic pressure. The beaker contains pure water, and the tube contains a 30% mass by volume sugar-water solution. A selectively permeable membrane is located at the bottom of the tube. This selectively permeable membrane contains pores through which the water molecules can pass, but the sugar molecules, which are larger, cannot pass. Water tends to flow from an area of higher water concentration to an area of lower water concentration in a process called osmosis. Therefore, in this example, water molecules will move across the selectively permeable membrane into the sugar solution because the sugar solution contains a lower concentration of water, 70% water versus 100% water. Water continues to move across the selectively permeable membrane into the sugar solution until equilibrium is reached. At equilibrium, water flows across the membrane in both directions at an equal rate. The movement of water into the tube is evidenced by the decrease in solvent height in the beaker. and by the increase in solution height in the tube. At this point, the solution within the tube has a greater pressure exerted on it because the height of the solution is greater than the height of the solvent. The greater pressure on the solution, which is due to the pull of gravity, is called osmotic pressure. As with the other colligative properties, the amount of change due to the addition of the solute is directly proportional to the molality of the solution. If the osmotic pressure of a system is known, osmosis can be prevented by adding a pressure equal to the osmotic pressure on the solution. In fact, osmosis can even be reversed if the amount of pressure placed on the solution is greater than the osmotic pressure. The process of filtering water containing many dissolved solutes across a semi-permeable membrane is called reverse osmosis. Reverse osmosis filtration systems may be used for water treatment at home, in industry, or out at sea. The basic design of a reverse osmosis system places a thin, selectively permeable membrane between two compartments in a filter. Applying a pressure to the solution that is greater than the osmotic pressure forces water across the membrane into a different compartment, leaving the large solutes behind. The water in this compartment is purified and ready for use. Suppose your teacher gives you the molar masses of 4 substances and an unknown substance. During your lab, you must determine which of the 4 substances your teacher gave you. How can you determine which substance it is? You can use your knowledge of colligative properties to experimentally determine the molar mass of an unknown substance. There are a few things you must know and do before conducting the experiment. First, weigh the solute to determine the mass of unknown solute to be used in the experiment. Next, make sure the solvent chosen for the experiment has known Kb or Kf values that you can easily obtain. In addition, measure the quantity of solvent to be used in the experiment. Since the colligative property equations use molality as the concentration unit, it is easiest to measure the solvent in terms of molality, moles of solute per kilograms of solvent. Now perform an experiment to measure a colligative property that will allow you to determine the molar mass of the unknown substance. In this experiment, 25.25 grams of the unknown solute is placed into 100 grams of water. Heating the solution reveals that the boiling point is 100.72 degrees Celsius. Subtracting the solution's elevated boiling point from the boiling point of pure water gives the change in boiling point. Delta TB equals 0.72 degrees. Use the chart to determine the boiling point constant for water, 0.512 degrees Celsius over molal concentration. Substitute the known values into the equation for molal boiling point. Then, rearrange to solve for molality. Doing the calculation, the molality of this unknown substance is 1.4 moles per kilogram. Now that molality is determined, calculating the molar mass is only steps away. The next step in solving for the molar mass is to break molality into its constituents, which are moles of solute divided by kilograms of solvent. Plug in the known values of this equation, which are molality and the mass of the solvent measured in kilograms, and you see that one variable remains. Rearrange the equation to solve for the number of moles of solute. At this point, you probably recognize that the mass of solvent is still in grams. Convert the 100 grams of solvent to kilograms using the conversion factor 1 kilogram equals 1,000 grams. Remember to show units and cross-cancel them throughout the steps to ensure that you are on the right course. this becomes a little tricky at the end. Make sure you write the units of molality so you can see that kilograms cross-cancel. Performing the calculation yields an answer of 0.14 moles of unknown solute. Remembering the components of molar mass helps derive the molar mass from the experimental data. The components of molar mass for the solute are mass of solute per mole of solute. In the previous scene, the number of moles of solute was determined to be 0.14, and the mass of solute was measured as 25.25 grams at the beginning of the experiment. Therefore, both values for molar mass are known. Plugging in the values gives the answer that the molar mass equals 180.36 grams per mole. Comparing this value to the 4 values given by the teacher, you conclude that your unknown is substance X. This concludes the Solutions program. You have learned about various aspects of solutions, including how solutions form and the factors that affect the rate at which a solution forms. You now know there are several ways to express the concentration of a solution, and that reporting the units of concentration is important. In addition, you've seen the effects of a non-volatile solute on the colligative properties of solutions. Now that you are familiar with the different types of solutions, you will begin recognizing how common solutions are in your daily life, both in and out of the chemistry lab.